Hi everyone, welcome to our last episode on our series in vectors. This is episode 3 and we'll be extending our knowledge of vectors into 3 dimensions and explore some of their applications. So far, we've encountered vectors in 2D on our x and y axis. However, the world around us is in 3 dimensions, so we now add our third dimension, which is the z-axis. This is the 3D plane. We can do all the cool things we did in the 2D plane in 3D plus many more. So in this episode, we'll be covering 3 major topics. 1. 3D vectors. 2. Vector equations of lines. And 3. Further applications. The awesome thing about vectors is that the properties of vectors in 2 dimensions generalize really nicely into 3 dimensions. Our basis vector in the 3rd dimension is k. So visually, you can think of k as a unit vertical vector. This means we can denote 3D vectors into basis vector form or column form with our 3rd component. For the length of a 3D vector, we just use the distance formula to derive it. A common mistake is to think that you need to cube root something, but we just need to apply the distance formula twice. For the midpoint of 3D vectors, we still just take the midpoint or the average of the 3 coordinates. Vector addition and subtraction is remarkably similar, but we just have to add or subtract our 3rd component separately as well. Now, recall the 2 formulas for the dot products. Firstly, if we have the individual components, then we just multiply each component together and add them all up. Secondly, if we have the lengths and the angle between the vectors, then our 3D dot product looks exactly the same. We still just multiply the lengths of the 2 vectors and cos of the angle between the vectors. Rearranging the dot product, cos theta is equal to this. If we take a dot product of a vector with a coordinate axis, then this is called a direction cosine, where theta represents the angle that a vector makes with the coordinate axis. So, for example, let's take a dot product of vector A and the x-axis, or vector I. Computing the dot product, and since the length of a unit vector is 1, the direction cosine is equal to the x component of vector A divided by the length of vector A. Similarly, the direction cosines of the y and z axis are the following. Finally, recall that a vector projection tells us the distance a particular vector B travels in the direction of vector A. The formula of a vector projection of one vector onto another still remains exactly the same. Now, what if we want to express equations of lines but with vectors? Say we want to find the equation of a line through the origin and parallel to vector B. The position vector B already starts from the origin. Then, a scalar multiplication of vector B will just be in the same direction but a different length to B. Thus, we can represent every point on that line as a scalar multiplication of b with another variable or parameter called lambda. For example, when lambda is 2 or 10 or minus 1/3, we can construct these 3 points. So, substituting every possible value of lambda will give us the entire equation of the line. Now, say we want to find the equation of a line through point A and parallel to vector B. We can start from vector A as the head of vector A lies on the line. Now, how can we reach all the other points on that line? Starting from point A, we just add different scalar multiplications of vector B and construct every single point on that line again. So we now finally have a formula for the equation of a line through one vector and parallel to another. Since we know vector A lies on that line, we call A the position vector. Since B tells us the direction in which it's heading, we call B the direction vector. So we can understand the vector equation of a line as starting from the position vector A and adding a scalar multiplication of direction vector B. Now say we want to find the equation of a line through 2 points, A and B. To extract the vector equation of a line, we just need to find the position vector and the direction vector. We can use either vector A or B as the position vector since they both lie on the line. Then we just need to derive the direction vector by calculating vector AB. Recall that the vector AB is the position vector B minus A, so this becomes the vector equation of a line through 2 points. This vector form of a line is called a parametric form because a parameter is just another variable used to define a relationship between x and y. But we are very familiar with dealing with only Cartesian variables x and y, so we derive the Cartesian equation by eliminating the parameter. For example, we have this parametric equation of a line. We first need to convert this into a column vector, which will allow us to equate the horizontal and vertical components separately. Now, using simultaneous equations, we can eliminate the parameter lambda, and voila, we have the Cartesian form of the equation of a line. For lines to be perpendicular, we require the dot product of the direction vectors to be equal to 0. We don't care about the position vectors since they only dictate the starting points of the lines. For parallel lines, we require the direction vectors of the lines to be equal to each other. In 2D, two lines will always either intersect or be parallel to each other. However, in 3D, two lines can be skewed. Skew lines are lines that do not intersect and are not parallel. To check if two lines are skew, we first need to check that they have no points of intersections. We again convert into column vectors, but now we will have 3 equations with 2 unknowns. Since we have more equations than unknowns, we solve lambda and mu simultaneously with 2 of the equations. Then we substitute the values of lambda and mu into our remaining third equation. If the values satisfy the third equation, then there exists a point of intersection at those values of lambda and mu. If the values don't satisfy, then they do not intersect. Finally, we just need to check that the lines are not parallel or that their direction vectors are not equal to each other. Then we can conclude that the two lines are skewed. Now, rather than defining the equation of a one-dimensional line, how can we define a 2D plane? Well, if you want to define a 2D plane, you just need to find 2 vectors that lie on that plane. Then the sum of the scalar multiplications of each vector will reach every single point on that plane. So this is the equation of a plane that passes through the origin and the 2 vectors a and b. But like lines, planes can be shifted up or down. So we can define a separate position vector p that the plane passes through. So this equation defines a plane that passes through the position vector p and parallel to the vectors a and b. For example, the YZ plane is the plane with the y and z axis that passes through the origin. So we set vector p as the origin, vector a as basis vector j, and vector b as vector k. The resulting vector equation is the YZ plane. So that's it for episode 3. In this episode, we extended our 2D concepts to 3D vectors, investigated different vector forms of equations of lines, and also covered some geometrical applications. And that's it for our entire series on vectors. I hope you enjoyed it and visit Intu for more information. So like, subscribe, and leave a comment below on what you would like to learn in the future. I'll be there.